Hello, in today's video I'm going to be giving an introduction to the idea of a derivative in the context of calculus. So let's get into it. Alright, so just recall from pre-calculus, rates of change tell you about how a function's values change, right? So if a rate of change is positive, that means a function is increasing. If a rate of change is negative, it means a function is decreasing. So there are two main types of rates of change that you should know. First, the average rate of change. So this is a slope of a secant line. Right, a secant line is a line where if you have a function, it intersects the function. Maybe it intersects more than once, but it goes through, that's not a very good picture, it goes through multiple points. So you have a point right here, a point there. It will go through both of those points. Now, on the other hand, instantaneous rates of change tell you the slope of tangent lines. So, let's say you have another function. Instead of it kind of intersecting the function at two places, it's intersecting once, at least locally. So it's kind of parallel to that point, or parallel to the function at that point. So an average rate of change, it tells you how the function would change if it changed linearly, right? If it changed by the same amount, it increased or decreased by the same amount over equal changes in the input. But that's not necessarily how functions always change. So average rates of change, that's why they're called an average, because they just give you how the function would change on average if it changed linearly. So the formula for an average rate of change, or slope, you can kind of think of it as slope, y2, minus, y2 minus y1 over x2 minus x1. So you take your rise over your run, your change in your y over your change in x. So delta y over delta x. Or you can do your change in your dependent variable over the change in your independent variable. So change in f of x over change in x. This would be f of x2 minus f of x1 over x2 minus x1. So there are many different ways you can interpret it. Really, it's just the change in y, or your dependent variable, divided by your change in your independent variable. Now, instantaneous rate of change, it's probably a new word, right? Basically, it's telling you, it's kind of in the name. Instantaneous, it tells you the rate of change at an instant instead of over an interval, right? Instead of being an average, it tells you exactly how the function is changing at a specific point. Okay, so that is the key distinction. With calculus, instead of looking at averages, looking at how a function changes on average, we're going to be looking at how a function changes exactly, right? Because there's a way to find out, you'll see, what the slope or what the rate of change is at a point. So we'll see that in a bit. Alright, so the instantaneous rate of change, like I said before, the average rate of change, you can think of it as a slope of a secant line, so a line that connects 2 points. Right, so this is kind of your interval where this is your x1, this is your x2. You're doing your slope formula. This is y2 minus y1, that's your rise. This is your x2 minus x1. So you're finding, on average, how it's changing over that interval from x1 to x2. On the other hand, the instantaneous rate of change, it tells you at some point, let's call it x1, it tells you how it's changing at that point. It tells you the slope of the tangent line, which intersects exactly, or not exactly, but intersects once, locally at least. So what that means is it could actually intersect multiple times. Like let's say instead of going this way, let's say the function, let's say it dipped down like this. Now this would actually intersect, right? But locally it only intersects once. So that's kind of what I mean. You can think of it, it's kind of parallel. You can see it looks like it has the same slope as the function at that point. Okay, so to approximate the instantaneous rate of change, you can use the average rate of change. So the formula for the average rate of change, as we saw in the last slide, you do your y2 minus your y1 over your x2 minus your x1. Or these are your function value 2 minus function value 1 over x2 minus x1. So what you can do is, let's say you want to find the average rate of change at x equals 3, right? That's what we're trying to approximate. You do f of 3 minus f of 2 over 3 minus 2. That gives you the average rate of change over the interval 2, 3. Now let's say you're doing it, let's say you want to get a better approximation. You shrink the interval towards 3. So instead of doing from 2 to 3, you do 2.9 to 3. If you want an even better approximation, you can do from 2.99 to 3, right? This approximation is only getting better and better as we shrink this interval. So it's getting closer and closer to the instantaneous rate of change. Alright, so say you want to approximate the instantaneous rate of change of f of x equals x squared at x equals 2. So we can do what we did on the previous slide, and we can use our average rate of change and just shrink the interval. So recall our average rate of change formula, AROC, which stands for average rate of change. That's f of x2 minus f of x1 over x2 minus x1. So you use this formula when you have function and you need to plug in the values. If you were given specific y values, you could use y2 minus y1 over x2 minus x1. But that is for specific x and y pairs. But here we're given a function and points. A function, and we're going to plug in points. So that's why we're using this formula. Anyways, so let's say for our first interval, let's go from 1 to 2. Okay. So this is going to be, remember, so our function is f of x equals x squared. So f of x, to get the function, you just take the input and square it. So our average rate of change for the first one is going to be 2 squared minus 1 squared over 2 minus 1. So that's, well, that top is going to be 4 minus 1, so that's 3 over 1. That's 3. All right, so let's say we want a little bit of a better approximation. Let's go from 1.5 to 2. All right, so we're shrinking that interval. So this is going to be, take 2, that's f of x2 minus f of x1, so 1.5 squared, over 2 minus 1.5. All right, so that evaluates to this is 3.5. Okay. All right. So let's say we want an even better approximation. Now let's go from 1.9 to 2. Okay, so we do f of x2, that's going to be 2 squared, minus f of x1, that's 1.9 squared, over 2 minus 1.9, that's going to be 3.9. So it looks like it's getting closer to 4. Let's do one final approximation, but this time, oh, that's not the way you write it. Even better. So let's do from 1.99 to 2. Alright, so we're going to do 1.99, or we're going to do 2 squared minus 1.99 squared over 2 minus 1.99. If you plug that into your calculator, or you evaluate that, that will be 3.99. So it definitely seems like it's going to 4, but we don't know for sure. That's what it seems like. It seems like it's about 4, but these are only approximations, so we can't say for certain. Alright, so to kind of visualize the process we were just doing, I have these graphs. So you see, for the first approximation, these points were pretty far apart, and we were measuring the slope of that secant line. So we do this is our rise, and then this is our run. So we measured this to be 3, and this to be 1. So we got a slope of 3. And then our average rate of change of 3, Then we brought the points even closer together. So as you can see, that gave us 3.5. And as they got closer and closer and closer, it seems like it's going to 4. And as you can see, it looks like it's approaching a tangent line. So this is the kind of the process if you're approximating instantaneous rate of change. You bring one point that you are not trying to evaluate at closer to another point that you are trying to evaluate at. So let's say you want to, like in this example, you want to find the rate of change at x equals 2. Then you have another point that you bring closer and closer and closer to, and you keep using that average rate of change formula to get better and better approximations as you bring it closer. Alright, so using the average rate of change formula and just shrinking the interval, we were able to approximate the instantaneous rate of change. But notice, this is only an approximation. How do we find the exact value of instantaneous rates of change? Well, to do this, we use something called a derivative. So a derivative, it's kind of a tool in calculus. It's very important. It helps to tell you the instantaneous rate of change or the slope of the tangent line at specific points. So in our previous example, we were able to approximate it by bringing them closer and closer together. So you might remember from the first video, if you watch that, bringing something closer and closer together, we have a tool for that. If you want to bring them so infinitesimally close, like there's barely a difference between them, they're getting very, very close but not equaling, use a limit. And notice the reason why you can't have it equaling, if b equals a, then you have f of b minus f of b over b minus b. That's just 0 over 0. That doesn't work. That's why you have to use a limit, so it doesn't actually equal. Okay? So we were kind of doing something similar to this, except for we were just approximating by bringing it closer and closer together. By using this tool that we learned previously, the limit, we can actually get an exact value. So this whole thing, this is just our average rate of change formula. Okay. Alright, so the previous formula that we just saw, that told us the derivative, or the instantaneous rate of change at a certain point. But let's say you want to find, let's say you want to plug in a point into some function and just find the instantaneous rate of change. That is what the derivative of a function does. So if you plug in any x value into the derivative, it will give you the instantaneous rate of change at that x value. So you say f prime. Yeah, by the way, derivatives are their notation uses this little prime symbol. I'll go over this in a little bit. There's other ways to kind of talk about derivatives, but this is one way of saying it. You say the function and then you just add a little prime or apostrophe. Yeah, this is read as f prime. And if you have this is f prime of x. And in this f prime of x is a function. So when you take the derivative of a function, you get another function that tells you the rate of change of that original function. And so the formula for the derivative of a function is f prime of x is equal to limit as h goes to 0 of f of x plus h minus f of x all over h. So I'll explain this formula in a minute. But try and just take a look at it and see if you can kind of understand why it works. Alright, so now I'm going to try and give some intuition for the derivative formula for a function that we just saw. So, let's say this is our function f. So let's say we have some arbitrary x value, and the output value at x for this function is just f of x. Okay. And then let's say we have another input value that is h units to the right of x. This value right here is going to be x plus h because it's h units to the right. So if we come up to the function, at x plus h, the function value at x plus h is just f of x plus h. You just take the function. You take f of x plus h. Alright, so now, if you notice, you can think of kind of the slope of the line that connects these 2 points, or the average rate of change between these 2 points. So, if you think of connecting those 2 points, the average rate of change, that's going to be our rise over our run. So our rise is going to be our y2, so f of x plus h, minus our y1. Because this right here, this is kind of our x1, y1, and this is kind of our x2, y2. And then our run, if you notice, this is h units to the right, so our x, our horizontal distance, is just h. So for very small values of h, this is going to give a very good approximation for the rate of change at x. But let's say you want to get the exact instantaneous rate of change of f of x at x. To do this, you use the limit. So get the exact instantaneous rate of change. You the limit as h goes to 0. So this little horizontal distance is shrinking. The limit as h goes to 0 of f of x plus h. So the limit as h goes to 0 of our previous formula. Because that's just taking our average rate of change, but then shrinking the interval because h is getting smaller and smaller. So that is kind of some intuition. And this is just some arbitrary value of x. This could be any value of x. So if you use the techniques that we used in the previous video to evaluate limits, you can often find, you can plug in whatever your function is. So if f is x squared, then you can plug in that for your function. So limit as h goes to 0 of or let's like x squared plus 1. So f of x plus h. So x squared or x plus h squared plus 1 minus x squared plus 1 all over h. So this limit as h goes 0. You can evaluate that using some limit techniques. Sorry, it's a little messy. And you can find an exact formula for the derivative. So if you plug in any x value, that'll give you the instantaneous rate of change. And you can do that because you learned the limits. That's why it's so important that you get the foundation of limits and continuity for calculus. That's usually why it comes first in the course. Alright, so now I'm going to give some kind of clarifications for some common things that people get confused on. So, the derivative, it's a function, right? F prime of x, that's a function. It's the derivative of f. But it can also be thought of an operator, right? Taking the derivative can be thought of as an operation. So let's say you're going from f to f of, f to f prime. You take a derivative. You use the derivative operator. And that might kind of just sound like jargon, like what am I talking about? It kind of ties into the next thing I'm going to talk about, d over dx. So there's different notations that you can use to talk about derivatives. So Lagrange's is the prime notation. So if you think about f prime of x or y prime, that is Lagrange's notation. Now Leibniz notation is d over dx or dy over dx. You can kind of think of it as change in y over change in x. But this d business, that's called a differential. That's like a very, very, very small, infinitesimally small. It means like very, very close to 0. Change in x or change in y. So that's what the d means. So it's kind of like delta x over delta y. But it's just over a very, very small interval. Anyways, so if you see something like d over dx of f of x, you're applying the derivative operator to f of x. But also, if you have something like dy over dx, that's just the derivative of y with respect to x. So x is your variable. And a lot of this, it's like very confusing. It's a lot of new information. As you go on in the calculus course, hopefully this starts to make more sense. But the key thing I want to talk about, let me just clear this up. The key thing I want to talk about is there's different types of notations you might see, but they really mean the same thing. So this is your primes. This is your d over dx. It's not necessarily super important that you know the names of them, usually, but it's just important to know that they mean the same thing. And also, oh, I accidentally removed some of that. That derivatives, they're a function, but they're also an operator. So you can apply the derivative to a function, and that gets you the derivative of the function. Right, taking d over dx of f of x gives you f prime of x. But also, f prime of x, that's a function, right? So there are multiple ways to think about them, think about derivatives, but they are very similar. They're all tied together. Alright, so now we're going to practice what we have learned. So we're going to do what we first did with approximating instantaneous rates of change. So let's say you want to approximate the instantaneous rate of change of f of x equals x squared at, instead of x equals 2, we're doing x equals 3. So the intervals that we're using this time are 3 to 4, 3 to 3.1, 3 to 0, 3 to 3.01. So for 1 second. So for 3 to 4, f our function is x squared. So to get our output, we just square our input. So we would do 4 squared minus 3 squared over 4 minus 3. That's going to be 16 minus 9 over 1. That is 7. All right, now just from 3 to 3.1. This is going to be 3.1 squared minus 3 squared over 3.1 minus 3. All right, this is 0.61 over 0.1. That's 6.1. All right, from 3 to 3.01. This is going to be 3.01 squared minus 3 squared, or 3.0 minus 3. This is 0.0601 over 0.01. That is 6.01. So it looks like it's going to 6, but we don't know. So let's now use our formulas that we use to find the exact value of the instantaneous rate of change. All right, so we're using the same function as before, but now we're going to use our formula for the instantaneous rate of change at a point to find that instantaneous rate of change exactly, instead of just approximating it. So, if you recall, f prime of a is equal to the limit as b goes to a of f of b minus f of a over b minus a. So here we're trying to approximate at a equals 3, right? So f prime of 3, our derivative at 3, is equal to limit as b goes to 3 of f of b. So our function is, we're squaring it, right? So b squared minus 3 squared, that's 9, over b minus 3. Okay. So if we plug in b equals 3, we can't really do a direct substitution because we get 0 over 0. And you pretty much always will when you're using these formulas. But we can actually factor this. So the top factors as a difference of squares. So this is 3 squared. So b squared minus 3 squared, that's the same thing as b minus 3 times b plus 3. All right, over b minus 3. Now, these b minus 3's will cancel because it's a limit. So this is a limit as b goes to 3 of b plus 3. And now we can use direct substitution to get 3 plus 3, which is 6. So our previous observation was correct. All right, so now we're going to use the formula we use for the derivative function, which is just the bottom right up here. Just so you can remember, f prime of x is equal to limit as h goes to 0 of f of x plus h minus f of x over h. So we're going to use that we're gonna find that, and then we're gonna plug in x equals 3 just to verify, right? Just double check. So here, f of x is equal to x squared. So we're gonna square whatever is in those parentheses. So limit as h goes to 0 of x plus h squared. That's just x plus h times x plus h. The reason why I'm writing it like that is because we're going to distribute it like that to find what that is. Minus x squared over h. Remember, keep the limit along for the ride. Don't drop the limit. All right, so this is x squared plus 2xh plus h squared minus x squared over h. Notice these x squareds will cancel. So this is the limit as h goes to 0 of 2xh plus h squared over h. So we can take an h out of pretty much everything. So this had an h, that has an h, and then this is h squared, so it has two h's. So this just becomes h. So this becomes the limit as h goes to 0 of 2x plus h. And now we can actually use direct substitution because we don't have any issues that will occur, right? We don't have a denominator that's going to 0. So we can plug this in. So that's just 2x plus 0, or just 2x. So that is our derivative of x squared. Okay, so now let's plug in x equals 3. So that would be f prime of 3 is equal to 2 times our input, which is 3, which is 6. So that all checks out. Alright, so now we have another function. F of x equals 7x minus 4. And we want to find the derivative of that function. Remember, this is all from first principles. We're going to learn some formulas in the next video that will help us evaluate this. But for now, we have to do this using our derivative definitions. So, if you're trying to find the derivative of a function, you basically always want to use this formula, which is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. It might seem hard to remember, but after enough using it, it becomes easier to remember. And you can kind of do what we did previously, where you have a function, you have some input value x, and then you go distance h along, and you can kind of reason to find the average rate of change, and then just take the limit as that goes to 0. Anyways, so our function is 7x minus 4, so this is going to be the limit as h goes to 0 of, so we're plugging in x plus h into our function definition. So 7x plus h minus 4 minus f of x minus 7x minus 4 over h. Alright, so this is the limit as h goes to 0 of, so if we distribute that, that's 7x plus 7h minus 4. And then this will distribute to both of those, minus 7x plus 4. So notice we have some really nice cancellations. Remember this, all over h. So these 7x's will cancel, and these 7h's, or no. And these 4's, plus 4 and minus 4 will cancel. So we're left with the limit as h goes to 0 of 7h over h. Because this is the limit, we can cancel those h's. And this is the limit as h goes to 0 of 7. The limit as h goes to 0 of 7 is just 7, right? We don't have any h's here, so it doesn't really matter. So f prime of x is really just a constant. it's 7. And that kind of makes sense because this is a linear function with slope 7. And linear functions, they have a constant rate of change. Unlike quadratics, unlike exponentials, they have a constant rate of change. And for this function, it's at 7. So that kind of makes sense that our derivative, which gives us the rate of change, will be 7. There's one more bit of practice. This is probably the hardest one. So we have a function g of x equals 2x cubed, and we want to find the derivative. So we're going to use our formula from before. I'm not going to write it out this time. Oh. So instead of using f, we're using g. So g prime of x, that's the limit as h goes to 0 of g, g of x plus h minus g of x over h. So g of x plus h, that's 2 times x plus h cubed minus 2x cubed over h. All right. So now, what you usually want to do when you have something like this, it's like just a power of x, even if it's multiplied by something. You want to find the expansion of x plus h to whatever power. So x plus h cubed, that's x plus h squared, or that's x plus h times x plus h times x plus h. If we distribute this first one, we get x squared plus 2xh plus h squared. That's what we got before, times x plus h. And if we distribute once more, it's going to be a bit bigger. If we distribute once more, we get x cubed plus x squared h plus 2x squared h plus 2x h squared plus h squared, plus x h squared plus h to the third power. And now we can combine some terms. So that's x cubed plus, we have a total of 3xh. And then we have a total of 3xh squared. And then we have an h to the third power. Or, sorry, we have a total of 3x squared h. Okay. So if we plug that back into our formula over here, so this is 2 times x cubed. How about, since these both have a 2, we factor out of 2 from the whole expression. So 2 times x cubed plus 3x squared h plus 3xh squared plus h to the third power minus x to the third power all over h. These x to the third powers will actually cancel. That's usually the pattern you'll notice, that if you have the derivative of x to the n, you'll have something like x to the n minus x to the n, so those will usually cancel. So this is the limit as h goes to 0 of 2 times 3x squared h plus 3xh squared plus h to the third power over h. So notice all these things have an h in them. So this had an h, this had an h squared, so that moves its power down 1. This had an h cubed, so this becomes an h squared. And then now this becomes the limit as h goes to 2 of, the limit as h goes to 0 of 2 times 3x squared plus 3x xh plus h squared. Now, if you notice, we have these h terms, but since h is going to 0, these are both just going to go to 0. So they don't really matter. And that's usually the pattern you'll notice if you do enough of these. So if we come over here for some room, this is going to become, since we took the limit, those go to 0, just 2 times 3x squared. That's 6x squared. Okay. Now, our second part is, for what values of x is the instantaneous rate of change of g equal to 12? So, we're trying to, the instantaneous rate of change of g is g prime of x. This is our derivative. And we're trying to find for what values of x is that equal to 12. So this is equivalent to saying we have our g prime of x. So equivalent to saying for what values of x is 6x squared equal to 12. If we divide both sides by 6, we get x squared equals 2. So this has two solutions actually. X equals positive square root 2, or just square root 2. And the other solution, which is x equals negative square root 2. So yeah, these are our two solutions. Alright, so I hope that the video was helpful. Hopefully it gave you some good practice on this. In the next video, we'll learn some techniques to find derivatives easier. But thank you for watching, and I hope that you have a good day.